Welcome everyone to the week one. So, in this week, we are going to have some background review of algorithms and data structure, and we will learn about the fundamental data structures, and we will learn about the asymptotic notations like big O, theta, and omega, and we will learn that how to analyze the algorithm's running time and how to perform the complexity analysis. Right? So, let's start with what is an algorithm. As all of us know, that algorithm is a step-by-step procedure to solve a problem. If I have to perform certain task, what steps we are going to follow to solve that problem, that is a algorithm. Algorithms are basically written in a plain English language, right? In the plain language, that how we are going to achieve our task, what steps we are going to follow. But whenever we talk about an algorithm, there are certain characteristics which should be followed. Like it may have zero or more inputs, it may have input, it may not have inputs. Output, it should produce at least one output. There may be more than one output, but there should be at least one output. Because if you are not getting any output, then how you can know that whether the task is accomplished or not, right? Or what you want to do if there is no output. So at least there should be one output. There should be definiteness. That means each process, each step is precisely defined. Each step is defined properly. Finiteness, that there must be a finite number of steps to achieve the output. Your algorithm should terminate after a finite number of steps. It should not have infinite number of steps. So the algorithm should be finite. And effectiveness. Each operation must be basic enough to be done exactly. That means whatever steps you are involving to get your output, that steps must have a role. It should be helpful in getting your output. So the each step, each operation of the algorithm must be basic enough to be done exactly, right? So just for example, if we go towards a very basic example of making tea. So if I'll ask you what steps do you follow? You will say we boil water, then we add tea leaves to the teapot, then pour boiling water into the teapot, steep for 3 to 5 minutes, strain into cup, and add sugar and milk if desired. So these are the steps, right? So it has a clear sequence of steps. If someone asks you how to make a tea, how to make the tea, you are going to give these steps. What are the inputs here? Water, tea leaves, right? These are the input. What is the output? Cup of tea. And it is a finite process because each step is getting you towards the result, and at the end you will get a cup of tea. So it is a finite process. It's not the infinite number of steps, right? So that is an algorithm example. Now, why we need to learn the algorithms? Algorithms plays a very important role in our real life. At every place we are using algorithms. Whether we need to search anything, we go on the Google, right, and we search it. In the background there is running a page rank algorithm, so due to which you see that why certain results appears first and certain results later on. So that is some due to algorithms. GPS navigation, whenever you need to go from one place to another place, we use the GPS and it shows you the shortest path, right? So that where there we are using the shortest path algorithms. Social media, we see the friend recommendation systems. The our Facebook shows us the friends recommendations. E-commerce, like if you buy a product, it shows you the recommended products, that what other products you can buy. In bank, there are fraud detection algorithms. So in everywhere, at every place in our real life, we use the algorithms. So that is why it is important to study algorithms, right? There. Now, when we create the algorithm, there are number of ways to achieve a certain task. There are number of ways to achieve a certain task to get a single output. Then which algorithm is the best one? which algorithm we should use. So we use the analyzing algorithm which help us that which algorithm is good to perform the certain task. Then we check it, we analyze it in terms of time and space. Time, how much time, computational time it is taking, and space, how much memory it is taking for execution. But here we will focus on the time complexity. The reason is we cannot you know we cannot means leave the time. The time is more crucial than space actually. We want our results quicker. As soon as I hit a button, I need my answer. So my algorithm should be fast enough in terms of time. We can sacrifice on memory basically, but we cannot sacrifice on time, right? So that is why we will focus, that space is also important, but the time is more important. So we will focus on time complexity at this time, right? So why we analyze the algorithms to, if we are having the different algorithms to perform the same task, to perform the same operation, then we choose the which one is the best one. That we do by using the analyzing the algorithm. Then comes out the RAM model of the computation, which is random access machine. It is a simplified computational model where instructions are executed one after the other. That means instructions are executed in sequential order. There is no parallel processing, there is no concurrency and nothing else. Each instruction takes a constant amount of time. Whatever instructions we are performing, that is taking a constant amount of time, and memory access also takes the constant time, right? So this model allows us to abstract away the hardware specifies and analyze the algorithm itself. Like for example, some machines may take more time to calculate the multiplication algorithm, but some machine may take the less time to calculate the multiplication, right? But we are saying according to the RAM model, the multiplication operation at every machine will take the constant amount of time. We are not dealing with the hardware, we are just dealing with the steps, the algorithm itself. Whichever is the hardware, we will not analyze in terms of hardware. Now, we have done the insertion sort earlier also. So insertion sort is in which we assume that our first element is sorted, and then we take element one by one and insert it at its proper position. So we start with the second element. So that is why my loop starts at here second. J equals to 2 to a dot length, where a is the array which we want to sort. Key equals to aj, that means the element which we want to put it at its proper position. Then we use a while loop to shift the elements to make the space for the element, and then we insert the element in step 8. We insert the element at its proper position. So which is the key? We insert the key at its proper position. This is the pseudocode. Now, if we have to analyze this algorithm, the time complexity, right? The running time here, look, the running time depends that how much time all of these steps will take in execution. How many times all of these steps will execute. So, sorry. Yes. So, the running time depends upon the input size and the input structure. Input size, that what is the value of n, what is the array size. Like for example, if you're having only 3 elements, one element, very less time. If you're having 10 elements, more time, but not very large time. If you're having 100 million elements, then it will take more time. So it depends upon the size, as well as it depends upon the structure of elements. Like for example, if your array is already sorted and you execute the sorting algorithm, it will take less time. On the other hand, if your array is sorted in reverse order, in descending order, and you want to organize your elements in ascending order, then it will take most time, right? So it depends upon the structure of input also. So let us count the number of times each line of pseudocode is executed. So let Ci be the cost of executing line I once. That means if we are at line number I, if we are at line I, the cost of executing that line I is Ci. And let Tj be the number of times the while loop test is executed for a given j. Right? Just for example, hmm, let me write. Okay. Just for example, we are saying if I'm having for I equals to 1 to 5 print. That means this print will execute, the print statement will execute 5 times, right? And the cost of executing this print statement, let's say, so the total cost becomes 5 times C, right? In the same way, let Tj be the number of times the while loop test is executed for the value j, and Ci is the cost of executing that. So the total cost will be C1n plus C2n minus 1 plus C4n minus 1. Let me show you. C1n, the statement executed, right? The first line executes n times. The for loop. This for loop will execute n times depending upon the length of the array. So it becomes C1n. Then C2n minus 1. This step, the cost of executing this step is C2, and this step will execute n minus 1 time. Because if your for loop is executing n times, then the inner statements of for loop will execute n minus 1 times, because the last time it invalidates the condition, right? So it will be C2 n minus 1, then C4 n minus 1. Again, this is the C4, so it becomes C4 n minus 1. Then we are having the while loop. C5 summation of Tj. The symbol is for summation, C5 summation of Tj, because this statement, we are saying it will execute Tj times, and every time the cost is C5. So C5 Tj. Now this statement will execute j minus 1 times, Tj minus 1 times, and this statement will also execute Tj minus 1 times. So it will be C6 times, and this will be C7 summation of. And at the end, C8 n minus 1. C8 n minus 1, this statement, C8 n minus 1. And if we add all of these values, we will get the total analysis, total cost. But this is really not helpful method. This is a very complex method because it is very difficult to analyze it, to compare it with other algorithms. So we need a simpler way to express it. So for that purpose, we use the order of growth and asymptotic analysis. So first of all, make sure that if my equation of the algorithm can be written in this form, like an square plus bn plus c, where n is the input size, then constants and lower level terms becomes less significant. That means we do not count c is a constant here, so we will leave this term. We are not going to use it. Bn and an square. N square is the high dominating term. N square is the dominating term, then n, right? So we will keep the n square. We will leave the lower order terms. So for the large value of n, an square term will dominate. So we will deal only this case. Then we discuss the asymptotic notation in 3 ways: best case, worst case, and average case. So best case is, like for example, in case of sorting, if your input is already sorted, so that is the best case. You need to do the least amount of work, right? Worst case, when your input is reverse sorted, that means you need to do the most of the work, right? Average case, which lies between best case and worst case, but generally we treat average case as the worst case. Now, So we use the worst case analysis, which is the most common, because every time we want to see how my algorithm will work in the worst case scenario. So the worst case analysis gives you an upper bound on running time, that what maximum time it will take for execution. Always we generally deal in terms of worst case, right? That it gives you upper bound on the running time, that it is crucial for systems where failure is not an option. Okay, then it gives you the worst time. Average case requires knowledge of statistical distribution of inputs, often difficult to define. And best case analysis is not very useful because it works only in the scenarios where you are known, that where the scenario is known to you, right? Like for example, I said if you're performing the sorting and your data is already sorted, but that is very rare, right? So we always deal, the most common is the worst case analysis, which gives us the upper bound on the running time. Now, you might be thinking that why do we care about the complexity? Look, time complexity help us compare and choose efficient algorithms based on their execution time growth with input size. Like for example, if your input size increases, how algorithm runtime will change. It predicts how well an algorithm scales for larger datasets, aiding the designing scalable applications, and it identifies and optimizes critical code sections, improving overall algorithm efficiency. Now, whenever the input size is very small, whenever input size is small, we generally do not care about analyzing the algorithm, that how much time it is taking, how much space it is taking, because that is manageable. But if your input data is so large, let's say n equals to 2 raised to the power 30. If your input data size is this much, then how much time it is take? How much time or how much memory it will take, space it will take, right? So then we need to consider, or then uh, we need to think about the complexity of algorithm. For example, suppose two algorithms A and B solve the same class of problems. Time complexity of A is 5000 n and one for B is 1.1 n for input with n elements. So that means for n equals to 10, the algorithm A will require 50,000 steps, but algorithm B will require only 3 steps. So B seems to be superior, right? Now, for n equals to 1000, however, A will require 5 million steps, while B will require 2.5 times 10 raised to the power 41 steps. That means there is a very much difference, right? That means we cannot use algorithm B for large data inputs. While algorithm A is still feasible, we can use it. So again, for whenever the number of elements are small, whenever the input size is small, we do not care about the algorithm generally. But when the input size increases, we need to think a lot. So we use the growth of the algorithm. Complexity is algorithm basically important, that how the growth of function is changing with the complexity, with the input size changes, and the growth of the time and space complexity with increasing input size n is a suitable measure for the comparison of algorithm. That means if we need to compare two algorithms, we check how with the input size, if the input size changes, how the algorithm's behavior will change in terms of time and space. And that is a key area how we analyze or how we compare our algorithms. That which one is the more efficient, which one is the best one. Again, so we said that we do the complexity by 3 ways: worst case scenario, best case scenario, and average case scenario. Worst case, where maximum number of steps taken for any instance of size n. Best case, minimum number of steps taken for any instance of size n. Average is average number of steps taken, right? So if we draw it in terms of a graph, the best, there is a, for problem size 1, your best case, worst case, and average case. all are taking the same number of steps. For problem size 2, best case is taking, let me draw using the pen. Yes. For problem size 2, this is a graph between problem size and number of steps required to execute it. So for problem size 2, the best case is taking minimum steps and the worst case is taking more. Then for problem size 3, the best case is here, again the minimum steps, the worst case is taking more. The average case lies in between somewhere. And you can see as the problem size is increasing, the number of steps are increasing, but worst case is always at the top because it takes the most of the steps. Best case remains at the bottom because it takes least amount of steps. So, how to perform the complexity analysis? So, exact analysis is really difficult, that how your algorithm will behave. So, we deal it in terms of upper bounds and lower bounds. And for that purpose, we use the notations big O, big omega, and big theta notation. We have a small o, a small theta, and a small omega notations also. But at this time, we will discuss about big O notation, big omega notation, and big theta notation. Let's talk about the big O notation. So, big O notation is it is a technique for abstracting away details of complexity, right? So we can use it for time and space complexity. So this is basically the main idea is that most important aspect of complexity is how fast it grows relative to the input size. So the focus is only on the growth rate, right? Coefficient only matters here if the growth rate is similar, and predicting behavior for small n is difficult for and often pointless. Let me tell you that how we do it basically. So big O notation. Big O notation, always remember, it works for the upper bound. That means the maximum, right? That how long, how far your complex for the base input size n, how far your complexity or an runtime of the algorithm can go. This shows you the upper bound. So it is in terms of definition, Fn equals to, where f is a function of n, Fn equals to big O of Gn if and only if there exist positive constants c and n naught such that Fn is less than equals to c of Gn for all n greater than equals to n naught. So we say that Gn dominates Fn. That means Gn is an upper bound of Fn. We say Gn dominates Fn, that means Gn is an upper bound of Fn if and only if these conditions are satisfied. There exist positive constants c and n naught such that Fn is less than equals to c of Gn. So if this is my function Fn, the algorithm, the point this one. So the upper point, this one, this is your big O, the upper bound. This is your upper bound from where it will start. Let me show you first example of big O, then we'll move on to big theta. So let us say that we are having a function fn equals to 2n plus 5. It's a linear function. And we claim that fn equals to big O of Gn. That means n dominates 2n plus 5. For certain values, n is an upper bound for 2n plus 5. So if you see as per the definition, Fn is less than equals to c of Gn for all n greater than equals to n naught, right? So we need to find out some constant Fn. The definition is Fn is less than equals to c times Gn for all n greater than equals to n naught, right? So Fn is 2n plus 5. That means 2n plus 5 is less than equals to c times n, because Gn equals to n here, right? So now We can say that 2n plus 5 will be less than equals to 2n plus 5n, right? Which means 7n, which means 7n. So 2n plus 5 will always be less than equals to 7n for all the values of n which are greater than equals to 1. So for all the values of n which are greater than equals to 1. So for the value of n naught as 1 and the value of c as 7, the value of c as 7, this definition is satisfied. For the value of n naught is 1 and c is 7, this definition is satisfied. So we say it is correct that n is an upper bound for 2n plus 5. Now we do just check it out and tell me that whether it is also correct to say that n square is also an upper bound, right? Okay. Then big omega, the big omega notation, this omega notation tells you the lower amount, at least minimum. Upper bound tells you the maximum, the upper bound, big O. Big omega tells you the least amount or the lower amount. That Fn equals to omega of Gn if and only if there exists a positive constant Cn and not such that Fn is greater than equals to C of Gn for all n greater than equals to n naught, right? So the minimum size. Now, and theta gives you the average case. The big theta gives you the average case, that is the upper bound and the lower bound. So it says Fn equals to theta of Gn if and only if there exist positive constants C1, C2 and n naught such that C1 Gn is less than equals to Fn, less than equals to C2 of Gn. That means you need to find out here two constants C1 and C2 for which lower bound as well as upper bound both exist. Theta gives you the more tighter bound because it gives you the upper bound as well as the lower bound. We did this example, okay. Now let's see the theta notation example. We say that function fn is given to us as n square over 2 minus 2n. And we claim that n square is the lower bound for this function. N square is the low a tighter bound. N square is the lower bound as well as upper bound because we are talking about the theta. That means we need to find out here two constants C1 and C2 and n naught such that C1 n square is less than equals to n square over 2 minus 2n, which is less than equals to C2 of n square. If we divide our equation by n square, it becomes C1 is less than equals to 1 over 2 minus 2 over n is less than equals to C2. Now, it means for n greater than equal to 1, because n has to be a positive value. For n greater than equals to 1, 1 over 2 minus 2n will be between 1 over 4 and 1 over 2, right? So we can choose C1 as 1 over 4 and C2 as 1 over 2 and n naught becomes 8. Right? So it is correct to say that n squared gives you the tighter bound or the theta notation for this one. If we see the omega notation, which gives us a lower bound. So let's say the equation is Fn equals to n square plus 2n and we claim that n square is a lower bound. That means we need to find out the value of constant C and n naught such that n square plus 2n is greater than equals to C times n square for n greater than equals to n naught. Now, n square plus 2n is greater than equals to n square, right? For the value of C as 1. If I put the value of C as 1, so n square plus 2n is greater than equals to n square for all n greater than equals to 0, right? So we can choose that C equals to 1 and n naught equals to 1. Since these constants exist, so we say that yes, this claim is correct. Now, whenever we are having the functions with different growth rates, how to compare them? Just always remember, constant is always good. Constant is the best actually. Then logarithms, then linear, then linear arithmetic, then quadratic, then cubic, and then exponential. So constants are always good. Always try to execute a algorithm in constant amount of time, or logarithmic or linear. Means it should be as least as possible. Big O of 1 means constant. Like if your example, for example, if you're writing the print statement, uh, if you're writing a print statement, then you're writing A equals to 1, B equals to 2, then you're writing C equals to A plus B, and then you're writing print C. We are using these 5 statements, right? And all of these statements, print C, and all of these statements will take constant amount of time. So it becomes 5. 5C. Since C is also a constant, so the total time is 5. Again, it's a constant, so the constant time is always written as big O of 1. 1 means constant time, which is less than the big O of log n, which is less than big O of n, which is less than linear arithmetic, that is n log n, then which is less than big O of n square, which is quadratic, then cubic, and then exponential. Now, let's do some examples. So first one is the simple loop. I'm using a for loop here, total equals to 0, which is a constant time, right? Then for I in range n, so there will be n iterations. Total equals to total plus I, which is a big O of n operation. So the total complexity of this one is big O of n, because we ignore the constants. Okay. Let's see. Okay, we have given in detail. So analysis. We are having here n additions, n assignments, and 1 return. N additions, this addition, n assignments, and 1 return, right? So exact time is 2n plus 1. Exact time is 2n plus 1. Because if you calculate is n additions, n assignments, and 1 return, 2n plus 1. Now, for 2n plus 1, if you calculate the big O notation, it will come out as big O of n. If you calculate the omega, do it yourself, it will come out omega of n. And theta notation, it will also come as theta of n. So that means this function grows linearly with the input size n. Then another example is matrix, the nested loops. For I in range n, for j in range n, print the value of ij. So the outer loop is executing n times, the inner loop is executing n times, and the print statement takes constant time. So if we are going to analyze it, n operations times n operations, that means n square operations, n square print statements. So the exact your function becomes fn equals to n square. Now if you calculate the big O, omega, and theta, all of these will come n squared. That means the number of operations grows quadrilaterally with value of n. One more example is sequential loop. That means first we are performing this loop which executes n times. Then we are executing a nested for loop which executes n times n, which is n square. So total operation here becomes n plus n square. First time n, then second time n squared. So n times n squared. So the function becomes n squared plus n. Now, if you calculate its notations, it will come n squared, n squared, n squared. That means again, because the one thing remember, n square will dominate n, right? N square will dominate n. So the complexities will come in terms of n square. Then this is the example of binary search in which we half our array every time. We divide our array in half every time. So the finding the element big O of 1, that is the best case. Worst case, element is not present, so that will be theta of log n, and average case will be theta of log n. This is an example with mixed complexity where we are using some constant statement, then constant statement. Then this is an example for logarithmic component because whenever you are dividing your array into halves, two halves, it becomes half log n. Then there is a linear component where we are using a for loop where it is executing n times. So the total becomes 1 plus log n plus n. 1 plus log n plus n. Again, if you see, the dominating term here is n because n is larger than log n. Dominating term here is n, so your answer will come big O of theta of n. One more example is for conditional execution. We are finding the linear search if array equals to z return. Otherwise, for I in range length of r, if array equals to target, return I. Right? Okay. Then again, this is a one-time statement. So big O of n, big O of 1, constant time. Then for loop executes n times. Then again it is one time, constant time. So the overall complexity comes out to be n. Right? Okay, big O of n. So that is the worst case. Best case is big omega of 1. That means you found the element at the very first time. So this is the best case. Right? Okay. So if we create this in summary, simple loop has a big O of and make sure it is not so that all these three complexities will be same for every example. These may be same, these may be different. Like for simple loops, big O, omega, theta all have the n. Nested loop all of have n square, sequential loop all of have n square, binary search. Big O is log n, omega is big O of 1 and theta does not exist for this. For mixed operations, it may be n, n, n. For conditional, it will be n, 1, not applicable, right? So these differs. So for this one, what we have covered, we covered about the algorithms. What are the algorithms? Why we study algorithms and why is required to analyze the algorithms, right? And the asymptotic notations. For all of these, you are supposed to study the chapter 1, 2, and 3 of your book, Corman, Analysis and Design of Algorithms, the Corman book, right? And if you have any issues, just come and meet me in the office hours, right? Okay, thank you. Bye.